There could be a planet Y, smaller than Earth, distorting the solar system's plane by 15 degrees. The average plane of the solar system is not perfectly aligned with the Sun's equator. There is a tilt of about 6 degrees between the orbital plane of the planets and the solar axis, a small but persistent deviation that has long intrigued astronomers. For a long time, this angle was attributed to the randomness of planetary formation. However, recent models suggest that something more concrete may be behind this asymmetry. An as-yet undetected object could be exerting continuous gravitational influence over the entire structure of the system. Unlike the Planet 9 hypothesis, which proposes a body 5 to 10 times the mass of Earth in an extremely distant orbit, the so-called Planet Y would be smaller, potentially comparable to Mars or even smaller than Earth. Its influence would not be on trans-Neptunian objects, but on the inclination of the orbital disk itself. Simulations indicate that a body with these characteristics, orbiting at a sharp angle relative to the ecliptic plane, could cause the type of distortion observed over billions of years. The mass wouldn't need to be enormous, it would only need to be inclined and stable enough. The difficulty in locating this object lies in a combination of factors: small size, low luminosity, and a probable position in a region of the sky rarely scanned by current surveys. Unlike gas giants, a rocky planet hundreds of astronomical units away reflects very little light. Even the most sensitive telescopes would have difficulty distinguishing it from the stellar background. This means it could have existed in the data for decades without being identified. Absence of detection does not equate to the absence of the object. Some researchers question whether the observed distortion is simply a residual effect of the migration of giant planets during the first millions of years of the system. The so-called nice instability, which describes the orbital reconfiguration period of Jupiter, Saturn, Uranus, and Neptune, may have left permanent marks on the disk. Others argue that this mechanism does not explain the angular precision of the current deviation. The debate between primordial causes and active influences has yet to be resolved. What makes the Planet Y hypothesis distinct is that it was not built to explain a single phenomenon. Instead, it emerges as a possible solution for multiple minor anomalies observed in the orbital planes of Kuiper belt bodies and beyond. When different datasets point in the same direction, the probability of a common cause increases. Still, none of this evidence is conclusive in isolation. The convergence of clues is suggestive, not confirmatory. Missions and surveys such as the Vera C. Rubin Observatory, currently in operation, were designed specifically to scan large areas of the sky with high sensitivity. If an object with the characteristics of Planet Y exists, it will be within the detection range of these instruments in the coming years. The current observational silence may have an expiration date, and if the object is found, the geometry of the solar system will need to be reinterpreted with it as a variable. A planet smaller than Earth, yet capable of bending the plane of an entire system, would be a discovery of historical proportions. There is an asteroid between Mars and Jupiter that has its own rings, and it shouldn't. The asteroid belt is generally associated with rocky, irregular, and inert objects. The idea that one of these bodies could have rings seemed reserved for giant planets. However, in 2015, astronomers confirmed that Chariklo, a smaller body located between Saturn and Uranus, possessed two distinct rings. Shortly after, similar cases were identified in other objects of the outer solar system. What no one expected was that a body in the main belt could exhibit the same phenomenon. The asteroid Chiron, technically classified as a centaur, possesses structures around it that behave like rings or, at the very least, as material organized in orbit. Observations were made during stellar occultations, when the object passes in front of a star and blocks its light. Variations in brightness before and after the central transit revealed the presence of additional material around the nucleus. This pattern is the same technique used to detect Uranus's rings decades earlier. The result was unexpected and still generates debate about the exact nature of the structures. The central problem is gravitational. Small bodies normally do not have enough gravity to maintain material in a stable orbit over time. The influence of Jupiter and Saturn, whose gravitational fields dominate the region, should disperse any ring within a few thousand years. The persistence of these structures raises questions about confinement mechanisms that are not yet well understood. One possibility is that particles ejected by cometary activity are continuously replenished, forming a dynamic rather than static ring. Another hypothesis involves the presence of small satellites acting as gravitational shepherds. The discovery also challenges traditional categories of planetary classification. For a long time, rings were treated as an exclusive feature of giant planets, the result of their enormous gravitational spheres of influence. Finding them in bodies with diameters of hundreds of kilometers forces a revision of this assumption. The physics that maintains them may be different, depending less on central gravity and more on local dynamic interactions. This opens the possibility that other asteroids, never examined with this level of detail, also possess similar structures. To date, observations of Chiron and Chariklo have been made indirectly through occultations, rather than direct imaging. This means the exact morphology of the rings, their width, density, composition, is still partially inferred. Computer models attempt to reproduce the observed brightness patterns to estimate the material's properties. The results suggest particles of ice and dust, similar to the material in Saturn's rings, but with distinct dynamics. Confirmation by high-resolution imaging still depends on dedicated missions or well-positioned future occultations. What the existence of these rings reveals, above all, is that the solar system still holds surprises in places considered well-known. The asteroid belt has been studied for decades, but most of its objects have never been examined with enough precision to detect subtle orbital structures. The discovery of rings in smaller bodies represents not just an anomaly, but an invitation to revise what is assumed to be impossible in planetary dynamics. The solar system has an invisible protective bubble, and it is being compressed by external forces. The Sun does not exist in isolation in interstellar space. Throughout its entire life, it emits a continuous stream of charged particles, the so-called solar wind that expands in all directions. This flow forms a plasma bubble around the system known as the Heliosphere. It envelopes all the planets, acts as a shield against galactic cosmic rays, and defines, in physical terms, where the Sun's direct influence ends. Its outer boundary, the heliopause, marks the frontier between the solar wind and the interstellar medium. The Voyager 1 and 2 probes were the first artificial objects to cross this boundary. Voyager 1 crossed the heliopause in 2012, Voyager 2 in 2018. Data collected during these crossings revealed a more abrupt transition than expected. The border between domains is thin, almost like a membrane. Beyond it, particle density changes drastically, and the magnetic field assumes a different orientation. These data are the only direct measurements humanity possesses of the solar system's limit. What made the results even more intriguing was the realization that the heliosphere is not spherical. Studies based on energetic neutral atom emissions, captured by the IBEX probe, suggest that the bubble is asymmetric, flattened in certain directions, thicker in others. One hypothesis is that the Sun's movement through the galaxy, combined with the properties of the local interstellar medium, is shaping its form. External pressure is not uniform, and this deforms the structure that protects us. The region the Sun is currently traversing in the Milky Way is called the local interstellar cloud, a relatively dense zone of gas and dust. Models indicate that tens of thousands of years ago, the Sun may have crossed a region of thinner interstellar medium, which allowed for a more expanded heliosphere. As the solar system moves into denser regions, external pressure increases and compresses the bubble. This compression could reduce its capacity to block galactic cosmic rays, with potential implications for the internal space environment. The relationship between the heliosphere and Earth's climate is still under investigation. It is known that galactic cosmic rays interact with Earth's atmosphere and can influence cloud formation and, consequently, the planet's albedo. In periods of a compressed heliosphere, exposure to these particles would increase. Paleoclimatic studies attempt to correlate periods of intense glaciation with the Sun's passage through regions of higher interstellar density. The connection is not established with certainty but is plausible enough to warrant continued investigation. This protective bubble, invisible to the naked eye and rarely mentioned outside scientific contexts, is one of the most important structural elements of the solar system environment. Its existence is what differentiates internal space, where the planets reside from the hostile interstellar space. Understanding its dynamics, size, and variations over time is essential not only for solar physics, but for understanding the environment in which life in the solar system developed, and the conditions under which it may continue to exist. Halley's Comet is one of the darkest objects in the solar system, and most people imagine it shines. Halley's Comet is probably the most famous astronomical object in human history. Records of its passage date back to 240 BC in China, and its periodicity of approximately 75 years made it the first comet to have its orbit accurately predicted by astronomer Edmund Halley in 1705. When it approaches the Sun, it develops a luminous tail that can be visible to the naked eye for weeks. This spectacular luminosity created a lasting impression that the comet itself is a bright object. But the brightness belongs entirely to the tail of gas and dust it emits. The solid nucleus that generates it is, in reality, extraordinarily dark. When the European probe Giotto approached Halley's nucleus in 1986 during its last passage through the inner solar system, the images captured deeply surprised scientists. The nucleus revealed itself as an irregular structure about 15 kilometers long by 8 kilometers wide, covered by a black crust with an albedo of only 0.04, meaning it reflects only 4% of the light it receives. For reference, asphalt has an albedo of around 0.04 to 0.05. Halley's nucleus is, therefore, as dark as road asphalt and ranks among the most opaque objects known in the solar system. This darkness is the product of a layer of carbonaceous organic material covering the underlying ice. Over billions of years of exposure to solar and cosmic radiation, organic compounds on the nucleus's surface were processed into dark, refractory polymers that absorb light efficiently. Below this crust, there are reservoirs of water ice, carbon dioxide, carbon monoxide, and other volatiles. When the comet approaches the Sun, the crust heats up and volatiles sublime through fissures, creating the jets that form the coma and tail. Halley's visible beauty is, in essence, the evaporation of an object that looks like coal. The density of the nucleus is another counterintuitive fact. Only $0.3 G/cm$3, less than water and much less than any rock. This indicates that the interior is highly porous, with large empty spaces between ice and dust particles. The structure is more like a fragile aggregate than a compact solid body. Comets that get too close to the Sun or Jupiter frequently fragment because they lack sufficient gravitational cohesion. Comet Shoemaker-Levy 9, which collapsed and collided with Jupiter in 1994, was a dramatic example of this process. Halley's next perihelion passage, the point closest to the Sun, is predicted for July 2061. By that date, several missions already under development may be capable of meeting it with much more advanced instrumentation than what was available in 1986. What Giotto revealed was just the beginning. The detailed composition, internal structure, and isotopic history of the nucleus still hold answers about the conditions of the primordial solar system. The most famous comet in human history could be, in 2061, the most scientifically studied of all time. All planets fit between Earth and the Moon. The average distance between Earth and the Moon is approximately 384,400 kilometers. For most people, this number evokes a vastness difficult to imagine. After all, the Moon looks close in the sky, but reaching it took the Apollo astronauts nearly 3 days. This same number, however, hides an astronomical curiosity that contradicts intuition. If Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune were lined up side by side, the sum of their equatorial diameters would fit, with room to spare, within that distance. The sum of the diameters of all the planets in the solar system, including Jupiter and Saturn, the largest, totals just over 380,000 kilometers. This means that all of them, aligned in sequence, would occupy less space than what separates Earth from its only natural satellite. The difference is small but real. A few thousand kilometers would be left over. Jupiter, with its 139,820 kilometers diameter, accounts for more than a third of the total alone, followed by Saturn at about 116,460 kilometers. The rocky planets, by comparison, are geometrically irrelevant in this sum. What this curiosity reveals is not just a property of the planets, but a fundamental characteristic of the scale of space. The solar system is, for the most part, empty. The distances between planets are immense relative to the bodies themselves. Neptune, the most distant planet, orbits more than 4.4 billion kilometers from the Sun, a distance that makes individual planets tiny compared to the spaces separating them. Gathering all of them into a single linear segment corresponds to compressing objects scattered across billions of kilometers into a tiny fraction of that space. This property also varies over time, as the Moon does not maintain a constant distance from Earth. At its perigee, the closest point in its orbit, it approaches to about 356,500 kilometers. Under this condition, the sum of the planetary diameters would no longer fit in the available space. At apogee, the distance reaches 406,700 kilometers, which offers a comfortable margin. The thought experiment, therefore, works on average but fails at certain moments of the lunar orbital cycle. This detail adds a dynamic layer to what seems to be a static statement. Beyond its appeal as a curiosity, this fact is a powerful pedagogical tool for conveying the scale of the solar system. It anchors an abstract comparison, the size of the planets, in a concrete reference that anyone can visualize when looking at the night sky. The Moon is there, visible, and thinking that Jupiter, Saturn, and all the others could fit in the space between us, and it transforms the abstract into the palpable. Astronomy rarely offers such direct shortcuts between the everyday and the cosmic. Miranda, a moon of Uranus, has a 20 kilometers high cliff, the tallest in the solar system, on a body the size of a city. Miranda is one of the smallest spherical moons known in the solar system. At only 470 kilometers in diameter, it barely exceeds the size of a large city. Because of this, when Voyager 2's images revealed its surface in 1986, what scientists found was the opposite of what was expected from such a small object. Instead of a smooth, inert surface, Miranda exhibited one of the most chaotic topographies ever recorded. Canyons, cliffs, terraces, and reliefs that seemed to have been assembled randomly. The scenery baffled researchers and remains partially unexplained. The most impressive element of this landscape is the cliff known as Verona Rupees. At about 20 kilometers high, with estimates even exceeding that value, it is considered the tallest wall in the solar system relative to the size of the body it is on. For comparison, Mount Everest is just over 8.8 kilometers high. On Earth, gravity itself limits the growth of vertical structures beyond certain limits. On Miranda, gravity is so weak, about 0.8% of Earth's, that the formation of a structure of this scale is physically possible without it collapsing under its own weight. The origin of Verona Rupees is still not completely elucidated. One of the oldest hypotheses suggests that Miranda was destroyed by a colossal impact and later reassembled haphazardly, with blocks of different ages and compositions piled without symmetry. This theory would explain the chaotic mix of reliefs but has difficulty justifying certain very well-defined structures. A more currently accepted alternative proposes that differences in internal composition cause subsidence and faulting in specific zones of the crust, generating cliffs and valleys through miniature tectonic processes. Miranda's surface exhibits at least 3 distinct regions called coronae, oval formations with concentric patterns of ridges and grooves that resemble racetracks on a geological scale. These structures suggest intense internal activity at some point in the past, possibly triggered by tidal heating due to orbital resonances with other moons of Uranus. The same mechanism that heats Enceladus and Io may have driven Miranda's geological activity during a specific period. After this resonance ceased, the body cooled and froze in its current configuration. A free fall from the top of Verona Rupees would last, under Miranda's gravity, approximately 12 minutes before hitting the base. It is not a lethal fall in terms of final speed, given the low gravitational acceleration, but it illustrates the absurd scale of the cliff relative to the physical conditions of the body. No other known place in the solar system combines a vertical structure of such magnitude with such low gravity. This makes Miranda a natural laboratory for studying the limits of planetary geology. Voyager 2 remains the only probe to have visited the Uranus system, and the images of Miranda were captured during a quick flyby that was not the mission's primary focus. This means much of Miranda's surface remains unphotographed in high resolution. A proposal for a new mission to Uranus, recommended as a top priority by the American Astronomical Community's Decadal Survey report for the 2030s, could finally reveal in detail what makes this small world so strangely complex. Iapetus, a moon of Saturn, is a world split in half. One face is 20x brighter than the other. Since its discovery in 1671, Iapetus has intrigued astronomers. Giovanni Cassini, who first detected it, noticed that the moon was visible when it was on one side of its orbit and disappeared when it reached the other. After decades of speculation, the explanation became clear. Iapetus has one extremely dark face and one extremely bright face. The difference in albedo, the ability to reflect light, between the two hemispheres is one of the most dramatic known in the solar system. The leading face, pointing in the direction of orbital motion, is as dark as coal. The trailing face is almost as bright as fresh ice. The division is so sharp that, observed up close by the Cassini spacecraft, it looks almost artificial. The dark hemisphere, named Cassini Regio in honor of its discoverer, has an albedo of about 0.03, absurdly low for any natural surface. The bright hemisphere, Roncevaux Terra, reflects much more light. The transition between the two is not gradual in all regions. In some places, the dividing line is relatively sharp, while in others, it is softer. This extreme asymmetry has generated hypotheses for centuries, and even today there is no unanimity on all the mechanisms involved. The most accepted explanation involves two combined processes. The first is external. Iapetus orbits Saturn in synchronous rotation. Just like the moon relative to Earth, it always shows the same face forward. Over billions of years, the front hemisphere accumulates dust and dark material ejected by other smaller moons colliding with meteorites. This material, of organic composition, is extremely dark. The second process is internal. The differential heating caused by the absorption of sunlight causes ice in the dark hemisphere to sublime and migrate to colder regions, making the dark areas even darker and the bright areas even richer in ice. The two mechanisms mutually amplify each other in a cycle of progressive separation. In addition to its dichotomy, Iapetus has another enigmatic feature: an equatorial ridge of mountains that extends for over 1,300 kilometers and reaches up to 20 kilometers in height. This structure, visible in Cassini probe images, runs along the moon's equator with disconcerting precision. Its origin is still unresolved. Some hypotheses propose it is a remnant of an ancient ring collapsing onto the surface. Others suggest internal subsidence or deformation from faster rotation in the past. Whatever the cause, it makes Iapetus even more unique among solar system satellites. The moon is also exceptionally large for a satellite of its class. At about 1,470 kilometers in diameter, it is Saturn's third largest satellite. Its orbit is inclined relative to the planet's equatorial plane, which is rare among large moons and suggests a different history of formation or capture. Iapetus orbits at a much greater distance than the other large moons, which reduced its interaction with material from the internal system and preserved certain primordial characteristics. Its distance and inclination make it a sort of isolated survivor from an earlier era. In astrobiological terms, Iapetus is less promising than Enceladus or Titan. There is no evidence of an active subsurface ocean, and the organic composition of the dark material is inorganic in origin, deposited from space, not biologically produced. However, the distribution and chemistry of this material provide information about the environment of the Saturnian system and how celestial bodies interact with interstellar dust over geological timescales. Iapetus is essentially an archive of Saturn's dynamic history recorded in black and white on the surface of a moon. Io releases more energy than all the power plants in the world. Io is the most geologically active object in the solar system. This statement alone would be enough to justify scientific interest. But the real scale of this activity exceeds any intuition based on earthly experience. Jupiter's moon emits a heat flux of approximately 100 trillion watts, a power equivalent to more than 5 times the entire installed electrical generation capacity of humanity. This heat does not come from residual radioactivity or a nearby star. It is generated by gravitational forces that continuously knead and stretch the moon. The responsible mechanism is tidal heating. Io orbits Jupiter in resonance with 2 other moons, Europa and Ganymede. This orbital configuration keeps Io's orbit slightly elliptical, preventing it from stabilizing at a constant distance. As Io moves closer to and further from Jupiter with each orbit, the gravitational force varies, physically deforming the moon's interior. This process is similar to what happens to a rubber ball squeezed repeatedly. Internal friction generates heat. In Io's case, the intensity is sufficient to continuously melt the rocky interior and feed hundreds of active volcanoes simultaneously. Io's eruptions are regularly recorded by ground-based telescopes and probes in orbit around Jupiter. Some volcanic plumes reach hundreds of kilometers in height, ejecting sulfur, sulfur dioxide, and rock particles into space. The expelled material feeds a plasma torus that surrounds Jupiter and interacts with its magnetic field. Io's surface is covered with calderas, lava fields, and sulfurous deposits in shades of yellow, orange, red, and white, the result of different compounds and deposition temperatures. It is visually one of the most colorful and violent worlds ever photographed. Compared to Earth, where volcanism is concentrated in subduction zones and hotspots, Io has no plate tectonics. Its interior is continuously churned by convection forced by tidal heat, and volcanic material resurfaces the moon on short geological timescales. There are no visible impact craters on Io. They are buried or obliterated before they can be preserved. This means the surface is one of the youngest known in the outer solar system, constantly renewed by fresh lava. The moon has the appearance of a living planet in a state of permanent crisis. Temperatures at Io's volcanic sources exceed 1,600°/circ/text $, in some spots, hotter than any contemporary earthly lava. This indicates that Io produces ultramafic magma, a type of molten rock rare on Earth today but common in the Archean Eon when the planet was younger and hotter. Studying Io, therefore, offers a window into geological processes that occurred on Earth more than 3 billion years ago. The moon functions as a geological time machine operating in real-time billions of kilometers away. The Galileo and Juno missions captured detailed images and data from Io, but no probe has yet been specifically designed to orbit the moon. The environment around Io is extremely hostile. Jupiter's radiation is intense enough to damage electronics quickly. The proposed Io Volcano Observer mission would aim to perform repeated flybys and map volcanic activity in detail without prolonged radiation exposure. If realized, it could answer fundamental questions about Io's internal structure and the limits of tidal heating as a geological engine. Titan, a moon of Saturn, has rain, rivers, and seas, but none of them are water. Titan is the only natural satellite in the solar system besides Earth that has a dense atmosphere and a complex, active climatic cycle. With an atmospheric pressure 1.5 times greater than Earth's, its surface is swept by winds, covered by dunes, and carved by rivers that empty into seas. At first glance, the landscape seems strangely familiar, but there is not a drop of liquid water on Titan's entire surface. The liquid that flows, rains, and accumulates in lakes is methane and ethane, hydrocarbons that, at less than $-179°/circ/text $, behave exactly like water in the terrestrial environment. The Cassini probe, in orbit around Saturn between 2004 and 2017, mapped hundreds of lakes and 3 hydrocarbon seas in Titan's North Polar region. The largest of them, Kraken Mare, has an area comparable to Earth's Caspian Sea. In 2023, images captured by the Cassini mission confirmed visible precipitation, methane rain recorded in real time by the probe's instruments. Studies published in 2024 confirmed that the seas have varied compositions and signs of tides, suggesting that methane interacts with ethane and heavier compounds in ways not yet fully understood. In addition to the methane cycle, Titan has a nitrogen-rich atmosphere filled with complex organic compounds called tholins, molecules that give the moon its characteristic orange color. These compounds form when solar ultraviolet radiation breaks down atmospheric methane and nitrogen, which then recombine into longer molecular chains. On early Earth, similar processes may have generated the first building blocks of life. Titan thus functions as a natural laboratory for prebiotic chemistry on a planetary scale. Titan's interior holds another surprise. Evidence points to a subsurface ocean of salt water, separated from the surface by a thick, icy crust. If this ocean exists and is in contact with a rocky core, the chemical conditions could be as interesting as those on Enceladus. Hypothetical life on Titan could inhabit two completely different environments. The methane seas on the surface, where organisms would use hydrocarbons as a solvent, and the aqueous subsurface ocean, where metabolism would depend on water. Neither has been confirmed, but both are scientifically plausible. NASA's Dragonfly mission, scheduled to reach Titan in the early 2030s, will send a nuclear-powered drone capable of flying through the atmosphere and landing in different surface locations. It will be the first time a powered vehicle explores another world with a dense atmosphere besides Earth. The primary goal is to analyze organic chemistry and check for conditions compatible with primitive forms of life. If Titan has the right molecules in the right places, the idea of life in alternative solvents will stop being philosophical speculation and become a testable hypothesis. Jupiter's Great Red Spot is a storm that has lasted for centuries, and it is shrinking. The Great Red Spot is the most iconic structure in the solar system after Saturn's rings. It is a persistent anticyclonic storm rotating counterclockwise in Jupiter's atmosphere, with winds reaching 600 kilometers per hour at its edges. Observations from the late 19th century estimated its diameter at about 40,000 kilometers, large enough to contain 3 Earths side by side. It is impossible to know exactly when it began, but consistent telescopic records date back to at least 1831, and older observations suggest it may be more than 350 years old. What has perturbed astronomers in recent decades is the realization that the spot is shrinking. Hubble Space Telescope data showed it has been decreasing by about 900 kilometers per year since at least the 1990s. At the beginning of the 20th century, it was large enough to accommodate 3 Earth-sized planets. Today, only one fits. The exact causes of the shrinkage are not yet fully understood. Some hypotheses point to changes in energy injection from the jet streams around the spot, while others suggest it is simply losing mass to neighboring atmospheric currents. The reddish color of the spot is another open mystery. Jupiter's gas is predominantly hydrogen and helium, but the orange and red hue of the storm suggests the presence of compounds like phosphorus, sulfur, or complex organic molecules that solar ultraviolet radiation may have chemically altered. Laboratory experiments simulating Jupiter's atmospheric conditions produced similar shades by bombarding mixtures of ammonia and acetylene with ultraviolet radiation. But no definitive explanation has been established. The color may be the result of multiple simultaneous processes operating at different cloud altitudes. The depth of the spot also surprised scientists. Data from the Juno probe, which has orbited Jupiter since 2016 and performs low-altitude flybys of the atmosphere, revealed that the storm extends up to 500 kilometers deep, much further than imagined for an atmospheric structure. This means it is not just a superficial phenomenon, but a three-dimensional structure with its own internal dynamics. The pressure and temperature in the deeper layers are extreme, and the physics that sustains the storm at that depth is different from what occurs in the visible layers. If the shrinkage rate remains constant, current models estimate that the Great Red Spot could become a compact circular structure, called a Little Red Spot, in a few decades. It may not disappear completely but rather change character. There have been historical episodes where the spot seemed to fade and then intensified again. What seems certain is that Jupiter will not run out of storms. The planet possesses dozens of other smaller anticyclonic systems, and the dynamic of merging between them is constant. The gas giant is, above all, a world perpetually in turbulence. Pluto has a giant heart of frozen nitrogen, and it controls the dwarf planet's climate. When the New Horizons probe flew over Pluto in July 2015, the image that captured the world's imagination was that of a heart-shaped structure on the dwarf planet's surface. Named Tombaugh Regio in honor of Pluto's discoverer, this formation is about 2,400 kilometers across and is composed mainly of nitrogen, carbon monoxide, and methane ice. Before the mission, it was expected to find a barren, uniform, and geologically dead world. What the probe revealed was a planet with water ice mountains as high as the Alps, valleys, dunes, and a thin but active atmosphere. The left lobe of the heart, called Sputnik Planitia, is a massive impact basin about 1,000 kilometers in diameter and 3 kilometers deep, filled with nitrogen ice. This ice is not static. It slowly convects in polygonal cells visible on the surface, like the convection of a heated liquid but on a geological scale. Pluto's residual internal heat is enough to maintain this slow movement, continuously renewing the basin's surface and erasing the impact craters that should accumulate over time. Consequently, Sputnik Planitia is one of the youngest known surfaces in the outer solar system. What made the discovery even more surprising was the confirmation that Pluto's heart actively controls the planet's atmospheric circulation. As the sun heats the nitrogen ice, it sublimes, turning directly from a solid to a gas, and migrates to colder regions where it deposits again. This cycle generates winds that influence the entire atmosphere. The basin's position, near the equator and at low altitude, is ideal for retaining and redistributing nitrogen. The heart is not a passive structure. It pulses climatically, regulating the planet's circulation like a continental-scale convection engine. The mountains bordering the heart reach 3,500 meters in height and are composed of water ice, a counterintuitive datum, as one expects to find frozen water in cold environments, but not in the form of structurally rigid mountains. At temperatures of $-230°/circ/text, see $, however, water ice behaves like rock, with enough hardness and strength to sustain high topographic structures for billions of years. Nitrogen and methane, being more volatile, form the surface layers, while water ice constitutes the solid substrate beneath. Pluto essentially has rocky ice mountains covered by nitrogen snow. Pluto's discovery by New Horizons was one of the most transformative moments in recent space exploration. No return mission is planned for now. The distance of more than 5 billion kilometers and the costs involved make any proposal technically challenging for the coming decades. But the data collected during the single 2015 flyby are still being analyzed and published. Each new study reveals an additional layer of complexity in a world the scientific community had classified as simple for 76 years. Pluto, demoted to a dwarf planet in 2006, took its revenge by proving to be more fascinating than many full planets. Mimas, Saturn's Death Star, hides an ocean that shouldn't exist. Mimas is one of Saturn's smaller moons, with a diameter of only 396 kilometers. Its most striking feature is a gigantic impact crater called Herschel, which occupies nearly a third of the moon's face and gives it an unmistakable visual resemblance to the Death Star from Star Wars. For decades, Mimas was considered one of the most geologically inert objects in the solar system, a frozen ball of ice with no internal activity, no fractures, and no heat sources. There was no scientific reason to suspect anything was happening beneath that heavily cratered, immobile surface. In February 2024, a study published in the journal Nature completely changed this perspective. Detailed analyses of Mimas's rotation and orbital data, collected by the Cassini probe, revealed a subtle oscillation called libration, incompatible with a completely solid moon. The movement pattern could only be explained by the presence of a liquid layer in the interior. Researchers concluded that Mimas possesses a subsurface ocean located between 20 and 30 kilometers below the surface, separated from the exterior by a thick, intact ice crust. The most surprising thing is not just the existence of the ocean, but its youth. Models estimate it formed only 2 to 25 million years ago, geologically recent for an object formed 4.5 billion years ago. This means the ocean is still in its early stages of development, heated by tidal forces generated by gravitational interaction with Saturn. Mimas's surface, filled with ancient craters, has not yet had time to record this internal heating in the form of fractures, fissures, or visible geological activity. The moon looks dead on the outside but boils silently on the inside. The discovery reinforces a lesson the solar system has repeated. Seemingly inert bodies can hide dynamic and potentially habitable environments. Enceladus showed this with its active jets and confirmed ocean. Europa showed it with its young, smooth surface. Now Mimas joins this group, but with a crucial difference. Its surface gives no external hint of internal activity. This raises an important methodological question. How many other icy moons in the outer solar system hide oceans we haven't detected yet because we don't suspect them? The next step in understanding Mimas would be a dedicated mission capable of precisely mapping the moon's gravitational and magnetic variations. But for now, no mission is approved to visit it. Data from Cassini, which ended in 2017, remain the primary source of information about Mimas. This case also illustrates the lasting value of grand exploration missions. Nearly a decade after Cassini's end, its data are still producing top-tier discoveries. Saturn's Death Star currently keeps its secrets under layers of ancient ice. Neptune has the fastest winds in the solar system, on a planet that receives almost no energy from the Sun. Neptune is the most distant planet from the Sun, orbiting at an average distance of 30 astronomical units. At this distance, the solar energy reaching the planet is about 900 times less than what reaches Earth. For this reason, it would be natural to expect a frozen, static, and atmospherically inactive world. The reality is the opposite. Neptune has the fastest winds ever measured on any planet in the solar system, reaching up to 1,800 kilometers per hour. For comparison, Earth's most intense hurricanes rarely exceed 300 kilometers per hour. The intensity of these winds on a planet so far from the system's primary energy source challenges conventional atmospheric models. The explanation for this paradox is not yet completely resolved. One of the most accepted hypotheses is that Neptune's internal heat, generated by the planet's gradual gravitational contraction since its formation, is an atmospheric energy source as important as, or more important than, the Sun. Neptune radiates nearly 2.6 times more energy into space than it receives from the Sun, meaning there is an intense internal source heating its atmosphere from the bottom up. This difference between energy received and emitted is proportionally greater on Neptune than on any other planet in the solar system. The winds are thus driven more by the planet's interior than by the Sun. Neptune's atmosphere is composed mainly of hydrogen, helium, and methane. Methane absorbs red light and reflects blue, giving the planet its characteristic color, which is more intense than that of Uranus, which has a similar composition. In the upper layers of the atmosphere, crystallized methane clouds form and move in chaotic patterns, visible in high-resolution images. The Great Dark Spot, observed by Voyager 2 in 1989, was an anticyclonic storm similar to Jupiter's Great Red Spot, but unlike it, it disappeared a few years after being discovered. Neptune seems to generate and dissolve giant storms with a speed Jupiter does not know. Deep inside Neptune, below the gaseous atmosphere, exists a layer of dense fluid composed of water, ammonia, and methane under extreme pressures and temperatures, so-called hot ice or the ice mantle. Under these conditions, water is neither solid nor gaseous in the conventional sense, but an intermediate state of extremely high density. There are hypotheses that, at these depths, the pressure is sufficient to break methane molecules and recombine carbon into crystalline structures. Essentially, it would rain diamonds inside Neptune. Laboratory experiments reproducing these conditions have already produced diamond crystals from methane, making the hypothesis scientifically plausible. Voyager 2, which passed by Neptune in August 1989, remains the only mission to have visited the planet. Unlike Jupiter and Saturn, Neptune has never received a dedicated orbiting probe. Proposals for a mission to the Neptune system have circulated in the scientific community, with an emphasis also on Triton, its largest moon, which orbits in a retrograde direction and may be a captured Kuiper Belt object with a potential subsurface ocean. The most favorable launch window for such a mission, using appropriate orbital geometry, will open around 2030. Neptune, the most forgotten of the giants, may be about to receive its first visit in 40 years.